talk about that. Thank you for coming.
Mr. Chairman, ladies and gentlemen, it's a great pleasure for me to speak here. I don't know why I have the honor for speaking in a plenary talk, but that's fine, so I have some more time. I want to thank the organizers for organizing this wonderful conference for us. I will speak on all-distances-twice rows. This is a certain class of tone rows. I will make some advertisements for these tone rows. These tone rows are a special case of these tone rows are the so-called all-interval rows. So at the beginning, I will tell something about tone rows. I will tell something about all-interval rows. Then I will speak about equivalence of tone rows. And then I will motivate why in these settings of equivalence, which I will suggest, which produces a little bit larger equivalence classes than Schoenberg's equivalence classes, I will show you why all interval rows are not good examples in my setting. And then we will come to all distances twice rows. And then we will see some of their properties. And finally, I will give some further generalizations of these ideas. So the first question, what is a tone row? Here's an example of a tone row, probably not an example which is usually in a book on mathematical music or in music theory. It's a tone row appearing in a piece for flute and piano by Olivier Messiaen, Le Merle Noir. And the flute is always playing the black bird. There are some cadenzas, and at the very end, the last part, the flute is also playing just some voices of birds, and the piano has such a very strict tone row. Here is this example of this tone row. And the first thing, for our analysis, the rhythm is not important, so we will omit all the rhythm. We just write down the different notes which appear. Moreover, it's usually done like this, that the special position of the notes is not important. So we can put the notes in an arbitrary position. What is important is that exactly all 12 possible octave equivalence classes are appearing exactly once. So from each tonality, let's say like this, octave equivalence class, exactly one note must appear in this tone row. So here I have the chromatic scale. So in the 12th scale, all the possible notes, it's just a small part of the 12th scale. Down you have the music. In the next position up, you have the numbers of the tones, maybe in the set of all integers. So this is a countable infinite number of notes, more or less. And in the second line up, you have just the numbers of the different octave equivalence classes. So in my notation, the 0 corresponds to the C, and the 1 corresponds to the C sharp. And then you see that these numbers of the octave equivalence classes are cyclically repeated from 0 to 11. So these equivalence classes, octave equivalence classes, they are also called pitch classes. And the pitch classes are forming a cyclic group, Z12, with the addition, or they are forming the residue class, ring modulo 12, Z12 with the addition and multiplication. And Z12 is just the set of this set modulo 12 set. It is represented by these 11 classes, 0 bar to 11 bar, but the bar up I will usually omit. And here is a circular representation of this cyclic group. We just arrange all these pitch classes in a cyclic way, as it is written here in form of the clock, or it could be a counterclockwise. It depends. I use the clockwise notation. And now coming back to the tone row. In music, a tone row is a sequence of 12 tones, so that different tones are not equivalent with respect to octave equivalence. In mathematics, we could write it as a function from the set 1 to 12. F of I is then the ith node of this tone row. It should do so that the tones have the labels in the set of all integers. And we require that the residue class of Fi, so the rest class of Fi, is different from the rest class of Fj when I is different from j. Or in short, we can use a bijective mapping from the set 1 to 12 into the set of 12 pitch classes. So in general, this will be my setting. A tone row is a bijective mapping from the set 1 to 12 into the 12 pitch classes. And f of I is in the pitch class of the ith note, in ith tone in that tone row. So once more, I express each pitch class occurs exactly once as Fi or as Fj. Exactly once. So coming back to our first example of Olivier Messiaen's series here, then here we have the reduction again. We see that all the different pitch classes occur exactly once. I was writing down just the sequence of pitch classes in my numbering. 9 stands for A, 2 stands for D, and so on. So now I want to show the circular representation of a tone row. Give me a tone row as such a function, f. We also write it as this vector, f of 1 till f of 12. For instance, again, our tone row. So then we are drawing this diagram with such a 12 gon. We are labeling the gon, the 12 vertices of this gon as it was done before. Then we indicate which is the first note, in this case, or which is the first tone. It is number 9. And then we connect the first tone to the second tone. So we connect it with an edge. We are connecting 9 with 2. And then we are connecting 2 with the third tone, what is 8, and so on. And finally, at the very end, we are connecting the last but 1 with the last, so we connect 5 with 7. So this gives such a circular representation of a tone row. So each tone row has such a circular representation, and the other way around, each circular representation, which is just walking through the graph, the circular representation of set 12 in such a way such that it meets every vertex exactly once, gives a tone row. So now what are intervals? Intervals are defined as differences in set modulo 12 set. So the interval from A to B is the difference B minus A. So it depends from which interval, so from which pitch class to which pitch class you're measuring an interval. Here are 2 examples. On the left side, we have the A up and the B down, and the difference of A minus B is then just the number of steps going in clockwise direction from A to B. So on the left side is 1, 2, 3, 4, if I didn't count wrong. And on the right side, we have the A down and the B up. And we have 1, 2, 3, 4, 5, 6, 7, 8. So in the left picture, the difference, so the interval from A to B on the left side would be 4, and on the right side it would be 8. And the interval vector of a tone row is now the following vector. You're just computing the intervals between consecutive nodes. So the first interval is the interval between the first and the second node. So f of 2 minus f of 1. The second interval is f of 3 minus f of 2, going on till to the 11th interval, f of 12 minus f of 11. And of course, these intervals you can also just find in the circular representation by just counting the steps from one tone of your tone row to the next. If we are starting from 9, then we see 9 is connected with 2. So from 9, we have the first interval, 1, 2, 3, 4, 5. Step 5. Then from 2, we are connected to 8. We have an interval of size 6, then intervals of size 7, and so on. So this is the interval vector. An all-interval row is a tone row where each interval occurs exactly once in the interval vector of the tone row. Obviously, the previous example was not an all-interval row. As we see, for instance, the interval 7 occurs twice. which intervals are allowed to occur? Of course, the intervals from 1 till 11, because the tones must be different. But here's another example of a tone row, which is an all-interval row. If we are looking, the first interval is just 1 pitch class up. The second one is 2 pitch classes down, but what is the same as 10 pitch classes up. The next is 3 pitch classes up, and so on. So we get the interval vector of this tone row as 1, 10, 3, 8, 5, 6, 7, 4, 9, 2, 11. So we see it is an all-interval row. So we are coming to the next subject, the subject of equivalence of tone rows. In general, in my simple model of tone rows, there are 12 factorial tone rows, 12 factorial different possibilities to write such bijective functions from 1 to 12 into Z12. This is quite a big number, and obviously several tone rows maybe share similar properties. And now we want to introduce certain equivalence relation on the set of tone rows. This, in order to get a better overview about the different kinds of tone rows, we are looking for a certain equivalence relation which is properly motivated, which has interesting properties of the different equivalence classes. The equivalence classes should not be too large, because when they are too large, then the tone rows in this big class probably are quite different already, so they will not share many common properties. On the other hand, also the equivalence classes shouldn't be too small, because then you're too close to the individual elements, and then you have maybe too many different representatives. So by introducing such equivalence classes, we're reducing the number of essentially different or non-equivalent tone rows, or we are reducing the number of different similarity classes. And the first equivalence relation which I introduce is this one given by Schoenberg, and more or less it is told that 2 tone rows are equivalent when one can be constructed from the other by a series of transformations like transposing, inversion, retrograde. So now I will just show in a few slides what are these different transversions. The first one is the transposing. Transposing of pitch classes means just you're adding 1, so you're adding the pitch class 1 to the pitch class I, then you get the pitch class I plus 1. This is transposing by 1 pitch class, or transposing by R pitch classes, where R can be an arbitrary integer. Is then just the addition I plus R to the R bar, so the R bar is again the pitch class of R. And transposing of a tone row means the composition of the tone row F, and so first you take the tone row, and then you apply the transposing operator. This is a composition of 2 bijective functions, so it gives again a bijective function, the transposed of the tone row. Here, for example, again our tone row from Monsieur, and then example transposing it by 1. You're just adding 1 to the pitch classes. 9 plus 1 gives 10 in first position, 2 plus 1 gives 3. 11 plus 1, of course, gives 0 then. And here's a graphical notation in musical notation. And what does transposing mean in the circular representation? In the circular representation, transposing means that you are rotating the graph of your tone row. So you see on the left side we are starting with 9, and then on the right side we are starting with 10, and the graph is just a rotation of the original graph. Moreover, we see that the interval structure of the rotated, the interval structure of the transposed tone row is the same as the interval structure of the original tone row. Moreover, actually the tone rows having the same interval structure as F are just the tone rows, or they enter the same interval vector as F are just those tone rows which can be obtained from F by transposing. And if F is an all-interval tone row, then also any transposed of f is an all-interval tonal. And then the next was inversion. Inversion can be written as either can be written in the form I, the pitch class I is mapped onto the pitch class minus I, or we have other kind of forms of inversions. They are of the form t to the power r, so an arbitrary power of the transposing operator composed with this upper inversion operator, and this gives then such a mapping. The pitch class I is mapped onto the pitch class minus I plus r. Graphically, inversions are always reflections, and inversions can in set 12 either have two fixed points or they have no fixed points. And here is an the example again of our tone row and the inversion of the tone row. Here in this case, we were doing some inversion at the pitch class 0. So the node C is, for instance, in the same place, and this is the inversion operator on the top, and this has then a second fixed point, which is then the F sharp, which is also in the same place, 0 and 6. And what is the inversion in the circular representation? The circular representation, it is just a mirror image. Here we see we have such a the mirror plane is going through the pitch classes 0, 6, for instance. And you can compute that the interval vector of the inversion, the interval vector of the inversion t to the power r composed with I of f is the inversion of the interval vector of the original f. So this means then if f is an all-interval row, then also the inversion of f is an all-interval row. Finally, the retrograde. The retrograde is just playing the tone row starting at the end and going to the front. So it is a permutation on the domain of the functions. This is written this permutation r up, which exchanges the first with the last, the second with the last but one, and so on. And if you compute f composed with this permutation, you get the retrograde. And here's the circular representation of the retrograde. And again, we see that we can compute the interval vector of the retrograde of an f from the interval vector of f by inversion and retrograde. And again, we see that if f is an all-interval row, then also its retrograde is an all-interval row. So we get that all tone rows equivalent in the sense of Schoenberg to an all-interval row are again all-interval rows. So together with my colleague Peter Lackner, who is also co-author of this paper, I was working on a long paper on tropes and tone rows, and in connection with this paper we were also setting up a database on tone rows, and in this database of tone rows we still consider a further operation in addition to transposing, inversion, and retrograde, which should produce equivalent tone rows, and this is a cyclic shift. So this we are considering then f composed with the permutation s. S is again the permutation on the domain of these functions, which just cyclically shifts through all the time positions 1, 2, 3, 4, 5, 6 till 12. So what is f composed with s? If f is again our tone row as in the previous one, then f composed with s starts with the second tone in the tone row, goes to the last tone in the tone row, and then at the end it puts the first tone of the tone row again. And so if you now compute f composed with s to the square, you are starting in the second position and so on. So you get all possible starting positions. So this gives now, so we consider all these 4 operations as similarity operations for tone rows, and then we determine the number of equivalence classes. Maybe you know with respect to Schoenberg's equivalence there are 9,985,000 and some non-equivalent tone rows. And if you consider now this bigger equivalence relation, then you reduce the number to 836,000 20,000 and some tone rows. And I was speaking about then how many tone rows are similar to a given one. So up to 576 different tone rows are then similar to a certain one. Of course, then it depends on the special structure of the tone row. There exist tone rows where this number is reduced. I have to think about the chromatic scale, so there will be much fewer tone rows. This is expressed by the stabilizer type of such tone rows. So a tone row is now called equivalent. F prime is equivalent to F if F prime can be constructed by any combination of transposing, inversion, cyclic shift, or retrograde. If you want to write it with these permutations in front, F prime is of the form some inversion composed with F, composed with some retrograde, composed with some cyclic shift. Yeah. The equivalence classes turn out to be orbits of the bijective mappings from Z12 to Z12 under the group actions of the direct product of two dihedral groups of order 24. So this product 24 times 24 probably gives them this 576. Here you see, maybe now I was still changing the domain. First we were speaking about the domain 1 till 12, and now I was changing to the domain 0 till 11 because of the cyclic shift. It has such a cyclic structure. This equivalence class, or this equivalence relation, was already considered by other composers and also mathematicians and theorists. According to my colleague, Josef Matthias Hauer, also was thinking rather in this aspect of equivalence of tone rows, starting with his composition Nomos Opus 19 in 1919, in which very many different tone rows appear. Then I want to mention Ron C. Reed's paper on combinatorial problems in the theory of music, where he just shows the same equivalence relation, or Gowomb and Welch. They are enumerating such polygons, just this, as we were showing them, these graphical representations. Hunt and Hippel are investigating symmetry in tone rows. And of course, here at the end, also my paper with Peter Lackner, which was in a special volume of the Journal of Mathematics and Music. What is the circular representation of an equivalence class of a tone row? So we are starting with the circular representation of the given tone row. In the next step, because of the transposing, we are deleting all the labels. Because of the inversion, we also consider its mirror image, or you're looking at the image in the left from the back, if you want. Because of the retrograde, we are deleting the first node. And because of the cyclic shifts, we are inserting the last missing edge. Yeah. So then this gives now a circular representation of the whole equivalence class of this tone row. Now back to interval vectors and all interval rows. Since now our tone rows are actually closed, we still have to insert a next interval. So after the 11 intervals, which were in our interval vector before, we still have to insert the last interval. This is the interval from the 12th tone in the tone row to the first tone again. So F1 minus F12. This way, now an interval vector is a sequence of 12 different intervals. And the interval vector of such a cyclic shift is then again the cyclic shift of an interval vector. So now when we are coming back to all interval rows, then it's easy to compute with the size of the final interval of this interval F1 minus F12. It occurs that it is just 6. In general, in an n scale, all interval rows can only appear when n is congruent 0 modulo 2, and then this closing, this final interval is always n over 2. So in this case, it is 6. So what does it mean? In our setting now, the interval vector contains each interval, but the interval to 6 occurs twice. So this is somehow is not such a nice property as it was in the Schoenberg property. Moreover, when you consider a tone row, an all-interval tone row, then not each cyclic shift of an all-interval tone row is again an all-interval tone row. Only those cyclic shifts are all-interval tone rows where the interval which stands in the last position is 6. And since there are 2 6 in the interval vector of an all-interval row, there will be only 2 versions, so one version and the cyclic shift of this tone row, which are actually all-interval tone rows. So in our setting, all-interval rows don't fit exactly into our setting. So what is the interval type? The interval type is a sequence of 11 numbers, A1 till A11, and A sub I tells that there are exactly I intervals in the interval vector of F. So the interval type of an all-interval row is now this vector. It tells one interval of size 1, one interval of size 2, one interval of size 5, 2 intervals of size 6, and then again one interval of all further sizes. Now what is the distance? Please remember when we were measuring intervals, we were just counting in clockwise direction from the first pitch class to the second pitch class, from A to B. And now, in order to compute distances, we are measuring in both directions. So I was now highlighting the pitch class on the top, and only the pitch class on the top has the distance 0 to the pitch class on the top. Then the following 2 pitch classes have a distance 1 to the top. So either the interval 1 or the interval 11 give the distance 1. Yeah, so these 2 pitch classes where the 1 is standing, they have distance 1 to the top pitch class. These 2 pitch classes have distance 2 from the pitch class up. So this is either interval 2 or interval 10. And now you can imagine distance is 3, 4, 5, and again 1 pitch class which has distance 6. And now we are replacing the intervals in the interval vector by distances, and we obtain the distance vector. So here on the top it's written 5, 6, 7, 7. This was the interval vector of Olivier Messiaen's tone row. And now we are writing down, instead of the intervals, we are writing down the distances. So 5 is 5, 6 is 6, but 7 corresponds again to the distance 5. Distance 5 is either interval 5 or interval 7. So this gives them the distance vector, 5, 6, 5, 5, 4, 2, 4, 1, 2, 6, 2, 2. And the distance type is now a sequence of 6 numbers indicating, BI is indicating the exactly I distances, no, the exactly BI distances of size I in my distance vector. Consequently, the distance type of this tone row up is 1, 4, 0, 2, 3, 2. This means, for instance, there's exactly 1 distance of size 1. Or there are no distances of size 3, but 4 distances of size 2. Is it right? 4, 4. No. Yeah, 2 forces. The distance vector is also known as an interval class vector. And distance types are sometimes also called Alan Furter's basic interval pattern BIP. And for instance, here this author, Zachary Kair, studied these interval class vectors and also these BIPs in his PhD thesis, Multiple Row Serialism in 3 works by Edison Denisov at the Eastman School of Music in Rochester. So what is now the distance type? This is still important. Distance types of equivalent tone rows coincide. So we can speak again of a distance type of an equivalence class. And the distance type of all interval rows now turns out to be 2, 2, 2, 2, 2. So this looks now nice again, because we have one interval of size 1, one of size 11. This gives two distances of size 1. We have one interval of size 2, one interval of size 10. So two distances of size 2 and gives the second 2. And we had we had two intervals of size 6, so this gives these two distances. And such tone rows which have this property we call now all distances twice. And now here's a list of all, it's a survey of all distances twice tone rows. Actually here I'm presenting the interval types of all distances twice rows. For instance, if we're looking at the first vector up, this means consider a tone row which has one interval of size 1, one interval of size 4, two intervals of size 5, two intervals of size 6, and so on. Then you get an all distance twice row. And here in the middle, in the second column, in the third line, is just again the interval type of the all interval rows. You can see this 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 1. So this is the interval type of all interval rows. And for all these other types, there exist tone rows. So all these types really occur as types of tone rows. And all these different types again give all distances twice rows. If we're looking what is written down in the last line, it is written down that with respect to this bigger equivalence class, there are 519 non-equivalent all interval rows. But now when you consider all distances twice rows, there are 4,162 different all distances, non-equivalent all distances twice rows. So there's a much bigger variety. Actually, in historic use, we realized that very many all interval rows were used by different composers. They were interesting for them, but hardly no other all distances twice rows. So this is a big field for composers to try such new rows. Now I want to speak about some properties. So I will speak about in general about the stabilizer of a tone row. What is the stabilizer of a tone row? The stabilizer is now a certain operation on the tone row. Operation means now combination of transposing, inversion, retrograde, or cyclic shift, which is applied to the tone row, and after applying this operation, you get again the same tone row. Yeah. So you apply such an operation to your tone row, and you get the same tone row. And such an operation is then called a stabilizing element, and the stabilizer is in the group of all stabilizing elements. And of course, there are many tone rows which have only the trivial stabilizer. This means only the identity does not change the tone row. Just only the identity. And whenever you take another operation, you get another tone row. So the majority of all tone rows has a trivial stabilizer, so no stabilizer. But there exist all interval rows which have a stabilizer of the form t to the power I, comma s to the power 6. This means a certain inversion of the tone row is the same as the cyclic shift by 6 positions of the tone row. Yeah, this ti this is such an inversion which doesn't have a fixed point. So the ti is just written down. It is just 0, 1, 2, 11, 3, 10. So this is such an inversion which doesn't have a fixed point. And now, if you apply ti to f from the left, what do you get? So you must compute ti of f. So ti, what is the image of 6 under ti? The image of 6 under ti is 7. What is the image of 3 under ti? The image of 3 is 10. And now if you're looking, and still not big enough, in the middle of the tone, you get this 7, 10, and so on. So if you are starting in the middle of the tone row, 7, 10, 2, 4, 5, 0, and so on, it's just this Ti of F starting at the beginning. Yeah, I hope you can see it. So this means this symbol stabilizer. So a certain inversion is the same as the 6 times shift of the tone row. This symmetry does not occur in Schoenberg setting, for instance, because it uses the cyclic shift. Another one is T6, R. This means transposing by 6 pitch classes is the same as the retrograde of the tone row. This is easy to see because transposing by 6 is just adding 6. So add 6 to 0, you get 6. Add 6 to 3, you get 9. It's the last but one pitch class. Add 6 to 10, you get 16, which is 4. And you get the second last but one from the back. So you see the transposed of this tone row, 6 pitch class is the same as the retrograde. And I also want to mention that these tone rows F, which I am writing down here, these are all interval rows. No? So here I'm speaking about stabilizers of all interval rows. All interval rows rather have poor stabilizers. Because of this asymmetry in the intervals, it's not possible to have many stabilizers. But for all interval rows, only these 1, 2, 3 possibilities occur. And if we now consider all distances twice rows, still another stabilizer can occur. This means then a certain inversion is the same as the retrograde. Yeah. On the top we had this inversion is the cyclic shift. And now here we have such tone rows where this same inversion is the retrograde. So if you apply Ti to this tone row, which is an all distances twice tone row, you just get the retrograde of this. For instance, the Ti of 2 is 11. The Ti of 7 is 6. And so you see this just, you can compute it. So all distances twice rows, they are a bigger set of tone rows, and you have a bigger set of stabilizers. No other types of stabilizers occur for all distances twice rows. So these 4 are possible. 3 of them are possible for all interval rows. So the next thing, probably here I forgot the S at the acoustics at the end, maybe, I'm sorry. What is an interval in physics or in acoustics? An interval is a frequency ratio. In an equal temperament octave, octave is a frequency ratio 2 to 1. This frequency ratio is divided into 12 equal parts. These are then the frequencies, and the frequency ratio of such a semitone is 1 to 2 to the power 1 over 12. So the 12th root of 1 to the 12th root of 2. Or if you take I semitones, then you must take this to the ith power. Normally, a tone row is not used in a vertical setting. Here I want to show you an example where a vertical setting appears. This goes back to Fritz Heinrich Klein, also belonging to this Schoenberg school. And he found the Mutter chord, the so-called mother chord, in 1919. This is a chord which contains each pitch class, and simultaneously each possible interval occurs exactly once. Yeah, so this is somehow, he was thinking about something where all the possible music is inside, all pitch classes and all possible intervals. So here it is written as a chord, and then here it is written as an arpeggio of this chord. And if you can read these notes, you will see that it is a tone row. And if you believe me in these numbers, you will see that all intervals occur exactly once. So this was probably one of the first occurrences of something like an all-interval row. Yeah. And I think when you're speaking about the chord, then it makes sense to consider intervals just counting in one direction, because intervals are always counting in one direction. But normally, a tone row does not occur like this in the music, but it just occurs like let's say, melodic line, so it had a smaller part of the. Here is again this tone row, all interval row, which we saw at the beginning as a possible interval, all interval row, such a mathematical construction, +1, -2, +3, -4, and so on. And if we're looking at this, we will see that all possible frequency ratios will occur. We have a semitone going up, 2 semitones going down, 3 semitones going up, 4 semitones going down, and so on. So we will have here all different powers of 1. So 2 to the power I divided by 12, all these frequency ratios. Of course, maybe going up or going down. Of course, there are still differences in the quality, but we have at least all possible representations. And now I'm just changing the position of some notes. I'm writing exactly the same notes again. Till to the C sharp in the middle, it's the same. No till to the G, it's the same. And then I'm reflecting, I'm going down with the D, for instance. And what can we hear now? Now we can hear a semitone up, 2 semitones down, 3 semitones up, 4 semitones down, 5 up, 6 down. But then 5 down, 4 up, 3 down, 2 up, 1 down. So we hear only intervals of maximum size 6, even though it is an all-interval row. So that what we hear heavily depends on the actual position of the notes in the system. So in an all-interval row, it happens that you don't hear all intervals. You hear some intervals several times. Now we consider an all-distances-twice row, which is not an all-interval row. On top is the row written, then we have the interval vector, 1, 1, 2, 4. So we see there exist, for instance, two semitones. So the interval type is 2, 1, 1, 2, 0, 2, 2, 8. Here's some. No, this 8 cannot be true. I'm sorry, with the 8 there must be something wrong. Yeah. So now I was writing down this tone row in a certain way. And if we're looking now, what intervals do we hear? We hear 1 semitone up, 11 down, 2 up, 4 up, 7 up, 8 down, 3 up, 5 down, 6 down, 10 up, 9 up. And now we see we hear all intervals. So it is not an all-interval row where you can hear all different intervals, because it is an all-distances-twice row. And this means all distances occur twice, and then you must play a little bit and then arrange the notes in such a way that you can hear all different intervals. Possibly Alban Berg's row from the lyrical suite from 1926 was influenced by Klein's mother chord, because it's exactly the same row which he was using. Berg was also using just the all-interval row from Klein. And maybe that was then a reason why all-interval rows were always considered rather as all-interval chords in the few. After this, all-interval rows became important and interesting, but they were always only considered measuring the intervals, as it is, of course, in set 12, it must be measured like this, but they were always rather considered as all-interval chords. And maybe this was then the reason why all-interval rows are so important in the history. But considering normal usage of a tone row, as I showed you, there is no essential difference between an all-interval row and an all-distances-twice row. You can arrange them so that you can hear all intervals or that you don't hear all intervals. That's why I make advertisements, write compositions with all-distances-twice rows. Hardly no of them are used. Now I want to give some remarks on the distance types. You know the distance type was such a vector B1 till B6. In the Pi is indicating there are Pi distances of size I in my tone row. Yeah. Or when you are looking at the universe of all tone rows in my database, you will see there are 2,785 different distance types. Only so many distance types can occur. No other distance type is possible. There are two non-equivalent tone rows having distance types where only one pi is different from 0, and then this pi must be 12. This is either the chromatic scale, which has 12 semitones, or the scale, so there's the sequence of all fifths or sevenths. So only these two distance types have only one pi different from 0. There are 180 non-equivalent tone rows having distance type with only two distances. So there are 138 different tone rows where only two distances occur. Well, I don't write them down now. You can find this on this database. There exist distance types where there's only one equivalence class of tone rows which has this distance type. For instance, these two above. There exists only the chromatic scale, for instance. Also here another one, if you take this distance type 0, 1, 0, 3, 2, 6, it's only represented by one equivalence class of tone rows, which is this one here. But on the other hand, look at this distance type. 2, 2, 2, 3, 2, 1. There are 5,464 different or non-equivalent tone rows having this distance type. So this distance type used to allow to construct very many different interval structures of tone rows. So this can be found using the database, for instance. Now still a few words about the generalization. Distances correspond to orbits of two sets under the dihedral group, for instance. Yeah? Or it could also work already under the cyclic group. The distance 1 is represented by this interval 0, 1. The distance 2 is represented by the interval 0, 2. And still to the distance 6 is the interval represented by 0, 6. And as you know from Alan Forter's prime forms and vectors of pitch class sets, there are just these 6 prime forms of intervals, of two sets. Let's call this like. So these normal forms of these two sets correspond exactly to the distances. So now we could go on, and instead of two sets, we could consider k sets. So we are considering now the first, second, third, and to the kth node of the tone row, and then consider its normal form. And then we go one step further. We start at the second and go to the k plus first node, consider this set, and consider again its normal form. So this means we choose such k between less than 12. Each tone row then determines 12 such k sets of consecutive pitch classes, because we have this closed form of the tone row again. So you get always 12 such different k sets. From each of these k sets, you determine the prime form. And then you can write down a vector of prime forms of these k sets corresponding to f. And then you can also count the different prime forms, how often they occur. And then you can also get something like the type of the prime forms of k sets. Actually, it is enough to consider k sets for k less than equal to 6, because the results for 7, they correspond to the results for 5, and 8 for the results for 4, and so on. So and here we consider a famous example, Alban Berg's violin concerto. This is this tone row up, 8, 11, 3, 7, 10. And it has the interval vector 2, 2, 2, 2, 3, 4, 4, 3, 3, 4, 4, 3. So here always only very small intervals occur. So actually the interval vector is the same as the distance vector in this case. And the distance type has 0, 4, 4, 4, 0, 0. This means We have 4 times the distance 2, 4 times distance 3, and so on, 4 times distance 4. And now I just write down the situation of 3 sets. So we consider now the sets of 3 consecutive pitch classes. Pitch class 8, 11, 3, then pitch classes 11, 3, 7. And we consider the normal forms of these. And I was just, now I was not computing the normal forms of 4. I was just using them in the lexicographic order of the normal forms of these 3 sets. And I was now writing just down a sequence of these normal forms. And then we see we get 5 different normal forms of 3 sets. These are these. The first one has the number 3. This is the number 5, 8, 10, and 11 in this sequence, according to the lexicographic order. And we see then that this, if you now just maybe still you have to rotate this vector a little bit, then you get this normal form of these prime forms of the form 3, 3, 3, 5, 10, 11, 10, 8, 10, 11, 10, 5. So this is now a generalization of the distance vector. Now it's a vector of the normal forms of 3 sets. And here is then a generalization of the distance type. This tells there are 3 times the normal. 3 times occurs the normal form 3, twice it tells the normal form 5, once 8, 4 times 10, twice the normal form 11. And actually this data are already computed now also for 3, 4, 5, and 6 for all possible tone rows, but they are not implemented in the official version of the database yet. But sooner or later it will be possible to search for something like this as well. At the very end, maybe not directly connected to this talk, I would like to ask or state a problem. I thought maybe there would be a blackboard or a white sheet to write something. Since there's nothing, I will just tell you like this. My colleague is also a composer, and for a certain composition of him or a plan of a composition, it would be necessary to solve the following problems. When we are considering now the hexachords, so the 6 chords, then you have Allenforte's list of all possible 6 chords. Yeah? Among these 6 chords, there are 26 chords which are equivalent to their complement. Yeah? So consider, for instance, the first 6 semitones in the chromatic scale, they are equivalent. So there exist 20 different normal forms of 6 chords which are equivalent to their complement. Is it possible to find representatives of each of these 20 classes so that when you're writing down all these 20 representatives, so in a long line, each pitch class will occur exactly 10 times? Yeah. Is it possible to find representatives of these 20 hexachords which are equivalent to the complement, so that each pitch class occurs exactly 10 times? This is an open question. Thank you very much for your attention. I'm sorry, you must speak a little bit slower. My English is not. Your speculation about the lyric suite. Yeah. And the climate. Yeah.
Is almost certainly correct.
Actually, it's a speculation of my co-author. Yeah. So.
Yeah.
For these things, he's responsible.
Berg set the poem, I believe it's by Theodor Storm. Schließe mir die Augen beide, twice, first in a kind of tonal setting, but then I believe his very first 12-tone work sets this using the row of the lyric suite.
Yeah.
And then, you know,
You're
but
right,
then at the very last measure, you know this.
Yeah,
there is the there is the Mutter accord played by the piano.
Yeah.
So I think
It occurs quite often.
Almost certain that there's
yeah.
the relation. Okay.
Yeah, thank you very much. It occurs quite often. We saw, because we also have musical information in our database, so you can search who was using this tone row, or who used a similar tone row.
You mentioned this Mutter chord as the possibly first occurrence of thinking about the all interval rows. To my memory, I found a book, but I forgot the author, and also there is a book on harmony, on modulation, a pedagogical book, where the intervals are the Keeler relations, and which was earlier in the beginning of the last century. And in the appendix, there is the recommendation to every day modulate through all 12 keys in another all interval row, together with a classification by a mathematician.
Interesting.
Yeah,
So thank you very much.
Anyone else? No?
Bob Peck is first. Not anymore. Bob Peck is first. Bob Peck. Bob. ¿Debo ayudarles a que se organicen ahí?
Ellos solitos se conectan. Préstame tantito el micrófono. Algo tenía que decir y ya se me olvidó.
¿De Harald? Del concierto de los autobuses.
Okay, very good.
You know Emilio?
You introduce him.
Yes. From here? Up there? Well, okay. Okay. I will, can you hear me? I will introduce Robert Peck as he sits up. Robert Peck is professor of music theory at Louisiana State University and coordinator of the music theory area. He holds the degree of Doctor in Music and Composition from Indiana University in Bloomington. His research specialization is in mathematical music theory, and particularly group theoretical and combinatorial models. From 2007 to 2012, he served as founding editor of the Journal of Mathematics and Music. Today he will talk about almost different sets in transformational music theory.
Thank you. First, I'd like to thank Harald Fripertinger for introducing much of the background information for this talk. Indeed, I think we could just probably skip my talk and and ask questions, because the two topics are